Hello.
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 Okay. Let me pull up the slides and we can get started. All right, so we have 2 chapters to cover today. So I didn't even make an attempt at a schedule. We'll just go through them, and then when it's time to take a break, we'll take a break. Yeah, good news is there's no, this discussion topic is related to the content for this week. So we'll just cover the 2 chapters and then go through the examples and then kind of go over what the discussion question is. So, okay, so today we're talking about regression, arguably one of the most commonly used tools in analytics. I use it nearly every day, especially if I'm on a program doing cost estimating. So it's important to get these concepts down, understand how they work, understand how to interpret a regression. I am really less concerned with the math as usual. So some of the slides have some formulas in them, but we're not going to spend a lot of time on those. It's more understanding the various concepts in the chapters and understanding how to interpret the results of regression analysis. So that said, regression analysis is the study of relationships between variables. We're trying to understand how the world operates or make predictions. And regressions use either cross-sectional data, so data gathered from the same time period from a population, or time series data, where we have one or more variables that are observed in different points in time. So I think we get into time series and forecasting later, and we'll talk more about autocorrelation later, but time series variables are interesting because they often can be regressed against their past. So there's a correlation between the past data for that variable and the future data, which makes sense. But okay, so in every regression study, there's some variable that we're trying to predict, and that's our dependent variable. You might also see a call to response variable or a target variable. And then explanatory variables, which in my field, we call them independent variables. Those are the variables we are changing in order to see if the dependent variable also changes in a consistent relationship. So we want to know if the independent variable, as it increases, the dependent variable increases by some predictable amount. If there's one variable, it's a simple regression. If there are multiple explanatory variables or independent variables, that's a multiple regression. Most models are going to use multiple. In cost estimating, sometimes we prefer, if we can, just a single. So if you're estimating the cost of some part of a ship or something for the Navy, like the engine, let's say, you could probably regress it against the weight, and so you'd have the weight of different engines for this particular ship from similar models, and then you would regress against that and see if the cost is related, and then if it was, you'd have a pretty solid prediction. You wouldn't need to add in more variables. So sometimes it's tempting to try to relate as many variables as possible to the dependent variable, thinking like the more complex the model, the better it will be. But that generally is actually the opposite. The more we bring in additional variables, the more we bring in room for error. Our prediction values tend to go down eventually. There's kind of like a sweet spot with the right number of variables, and we'll cover all of that in a little bit. But how do you know when to drop a variable, when to keep a variable? But complexity is not necessarily good. So and then also, when you have multiple variables in chapter 11, we'll talk about how you can have collinearity, and so that can mess with your regression as well, and we'll look at what that looks like with actual data. So we can do linear regression or we can do nonlinear regression. I think we primarily focus on linear regression. If we have a nonlinear regression, we often can translate the variables into log space or natural log space, and then do a linear regression on the log or natural logs. So we can, even if we have a nonlinear regression, we can often express it if we just transform the data. Okay, so the first thing to do when you're starting regression analysis is to make scatter plot, graphing X and Y variables. We've done this all semester. We haven't done it in the last couple of weeks, but we did it early on. We practiced making these graphs. So we're doing scatter plot, and then in Excel, we can click on our data and add a trend line and get a regression equation and formula and some information like the R-squared value. If there is a relationship between two variables, we generally can see it right away. So let's look at some promotional expenditures and sales from a pharmaceutical company. They've got 50 regions, metropolitan regions, and two variables. So their promotional expenditures as a percentage of the leading competitor, and their sales as a percentage of the leading competitor. So two indices. Note that those are relative calculations. Okay, so in Excel, we would graph our data, we'd select it, create a scatter plot, put sales on the vertical axis, and then promote on the horizontal, because the hypothesis here is that the large promotional expenditures will cause larger sales. So they believe there's a positive correlation between the two variables. Okay, we also have another example, which is overhead costs for this other company. So they have their overhead, machine hours, and production runs. And now we're looking at three variables. So we're going to compare the overhead versus machine hours and the overhead versus production runs. So we're still running simple regressions. We're just looking at seeing if overhead is better predicted by machine hours or production runs. So if we plot those, this is what they look like. This data, each row corresponds to a month. So technically this is time series data as well. We could graph by month the overhead and see if there's a pattern there. And then we could also check for relationships between the exploratory variables as well. So are machine hours at all correlated with production runs? And if you look at this scatter plot here, there doesn't appear to be a relationship. In this case, when we're looking at predicting overhead, we can see that there's some relationships. We just don't know which one at this point is better. This is a nonlinear relationship. So this is a scatter plot of life expectancy versus gross national product, I think, per capita for different countries. And we would hope to see a linear relationship, but this is a nonlinear. So you can see that there's a pretty strong curve here. Okay, we also have to talk about outliers. When we scatter plot our data, it will be pretty obvious if there are any data points that appear to be skewing our trend line and that don't appear to fit in with the data. So if it's not a member of the population of interest, then it's best to delete it. However, we can, if we're not sure, we can run regression with the outliers, suspected outliers in the regression, and then take them out and run it again and see how much the predictions improve. So like in this case, this outlier right here, got my little handy. Is the company CEO. So where our trend might appear to be going this way, this point up here is going to drag our trend line upward like this, making it less accurate. I need like a better tool. Okay. Another thing to note is unequal variance. So sometimes the variance of the dependent variable depends on the value of the explanatory variable. So if you look at the amount spent, what is this? The amount spent, spending data versus salary. There's clearly a relationship between salary and the amount of money spent on spending. But as we make, as salary increases, our variability also increases. So it's more consistent here. We're closer to the prediction line. And then as we move out, our variability increases. So this is unequal variance, and it violates an assumption of linear regression analysis, but we will look at ways to deal with it. Oh, that's hilarious. I gotta clear my drawings. Okay. Sometimes when we scatter plot data, we have no relationship. So just this shapeless scatter plot, we would not investigate this any further. So this is performance versus overtime hours. They're clearly unrelated. Okay, so I've used the word correlation a few times. Correlations are numerical summary measures that indicate the strength of a linear relationship between two pairs of variables. So they tell us how closely those, or how well one variable predicts another. And it's a single number. We call it, and here they are. So we can calculate this. The takeaway from this formula is that you're taking the difference between each data point and the average, and then you're dividing it by okay, so there's covariance up here, and then we're dividing it by the standard errors. So the numerator, this is the measure of the association between X and Y, and magnitude of covariance is hard to interpret because it depends on the units of measurement. So just be careful when you're looking at covariance alone. But when we're looking at correlation or covariance, the sign of it, so positive or negative, tells us whether they're positively correlated or negatively correlated. So positively correlated would mean as one increases, the other increases, and negatively would mean as one increases, the other decreases. And correlations are unaffected by units of measurement. So the correlation is always between -1 and 1, where 0 indicates no relationship whatsoever, and 1 would be strong positive correlation, and -1 would be strong negative correlation. So the 1 would mean that your linear relationship is perfect. You wouldn't see that. So and this is, we can only use correlation calculations for linear relationships. So we can get Excel to tell us the correlation. We look at the R-squared, and if it says, for example, like -0.86, that means that we have pretty strong negative correlation between the two variables, but only if it's linear. Okay, so our scatter plots and our correlations tell us whether or not there is a linear relationship and how strong it is, but doesn't quantify them. We can run simple linear regression to quantify a relationship between two variables only when we're doing one dependent variable and one independent variable. So we fit a straight line through the scatter plot, and generally we run least squares regression. So if this is our prediction line, then right here, a fitted value is the predicted value of the dependent variable. So some point along our line. And then this looks like a chart. Yeah, okay. So the difference between this observed value and the predicted value is our error. And we're trying to minimize that error between all the points. So the regression is moving this line around and then it's calculating the amount of error between each point and trying to minimize it, the total error. Okay, so a residual is the difference between the actual and the fitted values. So our observed value would be the fitted value plus the residual. So if we look back at our line, the residual is the difference between the two. And like I said, the best fitting line will be the line with the smallest sum of squared residuals, or the least squared line. When we run linear regression, we get a slope and we get an intercept. Our intercept is where the line crosses the y-axis, and the slope is the steepness of this line. They give you the formulas for slope. I mean, it's rise over run, if you remember from math a long time ago. And then you can solve for, if you know the slope, you can solve for the intercept by just plugging in two values into the y equals ax plus b equation. All right, so let's actually like run some regression output and look at what it looks like. So we're gonna find this least squares line for sales as a function of promotional expenses at Pharmex. On here they use stat tools, but we don't need to use stat tools. We can use, in our example, we just use Excel the way it is. All right, so this was our data. This was our initial scatter plot. If you remember, to generate it, we would insert scatter up here, and then we would tweak it a little bit to make it look nice. When we do that, we can then click on the data, add a trend line, and then select both display the equation and the R-squared value on the chart, which it's already done. And if you'll notice, when it displays the equation, it actually gives us the intercept here, 25.126, and it gives us the slope, which is 0.7623. So we have a positive relationship. I think that's as far as we're gonna go for now. Yeah. The strength of this relationship is not great. It's 0.45 is the R-squared. So it wouldn't be high enough for us to use it in the field, that's for sure. And then also, there are some functions in Excel that you can use. So you can actually run this intercept formula and get the intercept. So you can run it on your data. Same thing with slope. Same thing with the R-squared. And I don't even know what that is. I have never used those. I usually am running a full regression, and you get all of this information when you run regression analysis in Excel. So, but just so you know, if you just wanted one of those things, you could run it using one of these functions. Okay, let's also look at this overhead cost data. So actually, did we get, okay, so they also ran regression. I'm going to show you how to do this to get this output in a second. They also ran ran a correlation We've done that before to see if the sales and how strongly they're correlated. And then they plotted the residuals. So that's interesting. I think we're going to cover a little bit more about this later. Trying to think about why they. Okay, so for right now, we're just focusing on this information over here. So when you run the regression analysis, it gives you an intercept and it gives you the value of the slope. So we could derive the same equation, y equals ax plus b from this. So y equals 25.126 plus 0.762 times x. So the same equation comes out of this this analysis. And I guess for the residuals that they plotted for right now, the key takeaway here to note is like there's no pattern in the residuals. They're pretty, evenly spaced around the around 0 on the horizontal axis. So that's good. If our residuals have a pattern, it suggests that one of our regression assumptions has been violated, usually linearity. So just something to know. So to run this, you can select your data. Go to data analysis, select regression. Oh, it didn't, okay. So which way did we have it? Let's see. They had, do you guys remember which one they had on the, I already forgot, on the Y? I don't want to close out of it. I think I'm gonna have to. Okay. So we'll just select our values. And then we will ask it for the, actually just the residual plot. And you can put it in the same, or you can put it in a new workbook. And then when you run it, it'll pop up in a new workbook. I don't want to add to this one, so it'll pop up like it would have popped up in here, and it'll give you your regression results. This is actually a simplified, yeah, there we go. So you get all of this. So we have our R-squared value here, and then our regression equation information here. Also, note the intercept doesn't always have a very good p-value, but that's okay. We really are worried about this coefficient here for the independent variable, that its p-value is less than 0.05, meaning that this is a significant value and could not just be equal to 0. So that's something to note when you're doing regression analysis. You always want to check your p-value for your coefficients to make sure that it's significant. If you don't have enough data, sometimes that value will be too high. So you need to collect more data in order to establish whether or not there really is an actual relationship and you didn't just get a value by chance. Okay, so the overhead example for Bendrix is a multiple regression example. So we have two possible explanatory variables, machine hours and production runs. And so we can run it, in this case, they're running them separately, each variable separately. So if they ran by machine hours, they get this equation, and if they run by production runs, they get this equation. So this is our data. So when they run, oh, you know what, they didn't give me, yeah, okay. So this is the results for machine hours. So this is where they got the intercept and slope for the first equation, and then for production runs, this is where they got the slope for that equation. And if you look, both of these are pretty good. The residuals look good. They're centered around 0, and there's no obvious pattern. What else? P-value is good. The R-squared is not, 0.4 is not great. This one's even worse, 0.271. The p-value is good, but neither of these would be great predictors for machine, or for our dependent variable. So, okay, so we're trying to predict overhead. We have two kind of not great predictions, but for now, that's just how we're going to leave it, just to show you guys. So once again, to run these, you go to your data, you go to data on the ribbon tab, data analysis. We're running regression. Our Y in this case is overhead, so we select the overhead data. And then we're doing either machine hours or production. So for the first one, for machine hours, we would select that. And then we will ask it for our, I guess they're doing their residuals and the residual plots, and then we'd hit okay. And yeah, we'd get the same results that you see on these. So this is the output that comes out of running that. Okay, so the magnitude of the residuals is a good indication of how useful our regression line is for being for predicting. And we summarize the overall output for the residuals with a single numerical measure, which we call the standard error of the estimate. And that's S sub E. And it's basically the standard deviation of the residuals. So it can be calculated by hand, but we're not going to do that. And the same rules for standard deviation that we've talked about in the last few weeks apply to the standard error of the estimate. So it indicates the level of accuracy of the predictions made from that regression equation. Smaller is better. R-squared is the goodness of fit measure. It's one of the key things that you'll look at first. It's the percentage of variation that the dependent variable is explained by the regression. It's always between 0 and 1. And the closer it is to 1, the better the fit. So the equation's here, but just know in simple linear regression, R-squared is the square of the correlation between the dependent and the explanatory variable. So that correlation calculation that could be anywhere between -1 and 1, we square it so that we always get a positive value between 0 and 1. And when we go into multiple regression, it gets a little more complicated with the math, but for simple regression, it's just the square of the correlation. Okay, so for multiple regression, in our overhead example, we didn't get very good fits. So maybe if we tried to predict overhead by production runs and machine hours, we might get a better prediction equation. So now we're not, this is where in your mind things get harder. We're no longer fitting a line to a set of points. Now we have to go up in dimensions. So if we have one independent variable and two dependent variables, we're fitting a plane to a set of points in 3-dimensional space. Beyond that, we are in dimensions for which we cannot comprehend. So it's still doing the least squares method, but you wouldn't be able to, it would not be practical to do it by hand anymore. You really need a computing power to do that, because now you have you have both, the observed value is both off, not just in one dimension, but in two. So there's like along the x-axis and the z-axis. So it complicates everything. There is a slope term for each explanatory variable. And the standard error of the estimate and the R-squared summary measures are the same concepts apply. They're between 0 and 1. We want smaller standard error. We want an R-squared closer to 1. And we can include many types of explanatory variables in our equation. So when we're talking about regression coefficients, so if y is our dependent variable that we're trying to predict, then our explanatory variables or independent variables, x1 through xk, our regression equation would look as follows. So let me grab my little thing. So we would say y can be predicted by a, which is our intercept, which I just covered up, it's helpful, times b sub 1, so this slope b sub 1 times the variable x sub 1 plus some slope b sub 2 times variable x sub 2 all the way through. And these are the a and the b's are our regression coefficients. So each slope coefficient is the expected change in y when that associated explanatory variable increases by 1 unit and all the others remain constant. So the estimates of these b's here depend on what other variables are included in the equation. Meaning, if we drop this variable, the b's would change for the others. Okay, so let's go back to our example and let's try to predict overhead with machine hours and production runs. Okay, so if we were to do multiple, so let's go back to our data for a second, actually. Regression, we go to data, analysis, actually, we have to use am I blind? Shoot, they use stat tools, so I thought there was a way to do it. We might, okay, so they had to use that add-in, which is disabled on my thing right now, so I can't pull it up. But we would select y as our would still be overhead, but then we'd have machine hours as one variable, and then our other independent variable would be production runs. And when you run that, you get this multiple regression output. And so now look, we have an intercept and we have two coefficients, one for machine hours and one for production runs. So our equation is y equals 3,996 plus 43.536 times machine hours plus 883.6 times production runs. So to predict y, you would have to input both your machine hours and production runs in order to estimate how much overhead you're going to be using. The residuals look good. There's no obvious pattern. They're centered around 0. Look at our R-squared now. It's 0.866. So this is a much better prediction than either machine hours alone or production runs alone. So in this case, the multiple regression is justified. There's one other thing we need to check though. We would want to make sure that machine hours and production runs are not correlated together. And we looked at a scatter plot of them and they didn't appear to be, but we can also do a correlation matrix and look at the relationship between them, -0.229. So that's not a very strong correlation. There's some correlation there, but it's not terrible. We go in this chapter, we go back and forth between the same examples a lot. So I don't want to get ahead of myself, so I keep checking. Okay, so the output that you just saw, it looks very similar to the simple regression output. The standard error is the standard deviation of residuals like before, but now we have not just the number of observations, but also the number of explanatory variables. So that's the N and the K. The R-squared value is still the percentage of variation of the dependent variable that's explained by all of the explanatory variables combined, but it can only increase, so you can only improve the R-squared when you add extra variables to the equation. So the adjusted R-squared is an alternative measure, and it adjusts the R-squared for the number of explanatory variables in this equation. It usually is more conservative, and it kind of monitors whether or not those extra variables really belong in the equation. So let's see here, did we get, yeah, so there's our R-squared, there's our adjusted R-squared. They're pretty close, so that's good. Okay. Several types of explanatory variables can be included in regression equations. So we can have dummy variables, which we've talked about before a little bit, interaction variables, or nonlinear transformations. There's a lot of ways to model the relationship between a dependent variable and its potential explanatory variables, and it the more advanced techniques will produce better fits than we could get without them. But for the sake of practicality, we're not going to get into that. That would be a much more advanced course. So dummy variables are categorical, so they can't be measured on a quantitative scale. They're generally yes or no type of things, or like male, female. So 0, 1. Either you're one or the other. And so you could probably think of a time where some, like for example, let's say we're trying to predict salary, and we want to know if we can predict it, and we feel that gender is a good predictor of salary. So we would want that dummy variable in there, and we would make males either 0 or 1 and then females the other. And that would, that's how we would insert that categorical measure of gender into a regression equation. So generally we say 1 if it's in the category we're trying to observe, and 0 if it's not. So if we think the relationship is with one of the values, then we would set that value to 1. And we use these, so like the example I just gave you with gender, But you can also use them for like something like quarters, where you would have 4 categories instead of 2, but then you gotta do multiple dummy variables. So you do a dummy variable for each quarter. So quarter 1, quarter 2, quarter 3, quarter 4. So those would be your dummy variables. And then for like any particular data point, if it's quarter 2, then quarter 1, 3, so Q1, Q3, and Q4 would be 0, and then the value for Q2 would be 1. Does that make sense? So that's how you would do it for something like that. Okay, so we are going to look at an example using gender to predict salary. So we have all this data. This looks a lot more like the kind of data that you guys are going to be working with, especially when you do your final project. You're going to have some categorical values, you're going to have some numerical values, all kinds of things going on. Okay, so for the first note here, the example in the book will tell you what these things mean. Education is education level where 1 is finished high school, 2 is took some college, 3 is bachelor's, 4 is some graduate, 5 is graduate degree. Grade is current job level, 1 through 6. Doesn't specify more than that. Years 1 is years of experience with that particular bank, and then years 2 is the number of years work experience at another bank. Age, gender. PC job is a categorical yes, no, depending on whether their job involves computers. So you could easily translate this into a dummy variable by making the value 0 or 1, where 1 is yes. If you decided you wanted to measure salary against, say, see if there's a factor that into your regression equation. Female years 1, let's see, age, gender. Okay, so this is a calculation. If male, or sorry, if the gender is female, then use the value in D2, otherwise say 0. So they created this variable so that it zeroes out any employee who's not female. And then the log salary is the natural log of the salary. And I think we'll get into why they did that later, but these two are calculated variables. So this was the original data. Okay, another thing to note, so education is coded as if it were numerical, but it's not. So if you wanted to regress against education, you would need to create dummy variables instead. So you would need, like, in this case, you create a variable that's like high school, some college, some graduate, and then you 0, 0, 0, 1, 0, 0, like 1 being for that row, that employee corresponding. The reason is because we can't treat this like numerical because it's not. It's technically categorical. If you treated it as numerical, you'd be implying that the value is like, it's hard to explain, scalable, I guess, and it's really not. It's just a same thing as like gender, you know, how many years of school do you have? Okay, anyway. So we want to see if this bank discriminates against females in their salary. You could just compare them and say, oh, well, I took the average of females and males and they're different, so they do discriminate. You could also break it out with pivot tables by grade and see if that further shows like a big difference. This is only part of the story, so we're not seeing the effects of other variables in these pivot tables, but we can see that, like, as grades increase, it does appear that women are less likely to be in those higher grades. So that's something worth noting. But it's still not the full example. Okay, so let's run some regression. Oops, I went too far. Okay, so in this first attempt, they're going to compare their years. What do we got? Years of experience with the bank, years of experience at the prior bank, and look at salaries. And it looks like so the residuals are a little interesting here. That's worth noting. We get our values are okay, our coefficients are okay, but our R-squared is pretty low. So this regression is not a good predictor. Gender and years experience is not a good predictor of salary. Let's see. I'm trying to see how far we can do the second one. What did we do here? Okay. Now we're running a whole bunch of things. Years of experience. Okay, so look here. Remember I told you you can't treat education as numerical, but you could make it into a dummy variable. So it looks like that's what they've done here. And then gender. All of these are still okay. If one of these had a really high, actually, this p-value would lead me to think that I might need to drop this variable. So it's just something to watch. That's above 0.05. So this category, education 4, is probably not really contributing to the prediction in a statistically significant way. But look at our R-squared now, it's 0.645. So when we look at years of experience and education level and gender, we can predict salary a lot better. And then I think this is for another, oh, okay, and then they did everything. Now we have problems. I think they did this just to illustrate what's happens to the R-squared. See how we added variables, but our R-squared improved, but that may not be a valid improvement because likely in here somewhere, which this is making my eyes bleed, there's probably 2 variables that are correlated, and these 2 are questionable to include in the equation because of the p-value. So, but it is interesting to see. So now they've regressed it against everything, but look at our residuals as well. This is a concerning pattern. So there's something going on here. We would not blindly accept regressing again, or like predicting against all of the values. And likely what this means, so when you add in variables for a set of data like this, and you just keep shoving in different variables trying to improve your prediction, you will improve your prediction for this set of data. But if you were to add in new data, it likely would be terrible at predicting. So you've basically fit your prediction equation to like a very specific set of data, and you've created, if you think about how many dimensions we're talking about here, what do we have? 15 dimensions. Like, obviously we can't envision 15 dimensions in space in our head, but you've created this like obscure 14-dimensional thing in 15-dimension space that fits your data really, really well. But then when you go to predict new information, it's going to be terrible. And so we would call this data set like our training data. We're trying to train a regression against this, but then we would put in validation data. So data that we either pulled aside from our main data set to run in our equation and see how well it does with new data, or we would go collect more data and see if we can predict with the same accuracy. But the more variables you add, the less likely that is to be true. So it's very easy to get a good regression with a fixed set of data like this. In practice, we would split our data into training and validation sets, and we would compare. So we would aim for a good, decent regression for our training data, and then we'd run the validation and we'd hope that they were close. But sometimes they end up being garbage at predicting against new data. So it can be tempting to add in everything under the sun, but it won't help us. Okay, so let's talk about, also, some of these variables, and you can go back, and the example is pretty long, you can go back and read through them, but some of these variables like PC job don't really make sense for what we're trying to predict. So when you are considering variables, like you need to consider whether or not that even makes sense. But the point here is just to look at like what happens when you just dump all the variables and regress against everything. Okay, so like I said, they created those dummy variables, and then they were able to run these regression outputs. That's getting a little too far in the weeds. Okay, so in the stat tools thing, and I welcome you guys to go enable stat tools, because I'll downloaded it at the beginning of the semester and actually run the multiple regression along with the examples. So because we had these dummy variables, we have these, they call them interaction variables. Because we have the male and the female, the males are zeroed out, and we if we like ran the regression with one or the other, we'd get different lines. But so you can add in another variable to like force those lines to be parallel, but it's actually okay to allow them to have different slopes. So what that looks like, stat tools will implicitly create them whenever you have a dummy variable, and you just tell it which variables are category variables. And then what it does is it gives you the regression equations for the two different variables. So instead of just getting the one regression equation for female salary, we get another where it runs it for the male salary. So this is salary based on years of experience, it looks like, at that bank. So this is telling. That would be worth exploring. Okay, I point out that some of the variables looked like they might have been fanning out a little bit. And in that case, it might be worth exploring a nonlinear transformation. So when we want to do linear regression, which is what we're doing in Excel, we want this nice equation. We can take nonlinear data and we can make it linear by applying a transformation to it. So either taking the natural log, the square root, the reciprocal and the square, I almost never see anything but taking the natural log. So they do this with example 10.4. They take their demand versus cost for electricity. And they're trying to see whether the cost of supplying electricity is a nonlinear function of demand. So it's interesting that they chose this particular example, but that's okay. I would have liked. Okay, here's your power data. Originally, it's just the month, the cost, and the units. When you plot it, there's something going on. Just looking up here is a little wonky. It doesn't look fully linear. It actually looks quadratic. So that's what they did. They applied a quadratic trend line and they get a pretty strong correlation. A linear fit wouldn't be terrible with this set of data, but it definitely curves, and that's worth noting. And it should, because now we're talking about the cost of energy, so we have economies of scale. They also apply like a log trend line to this, and they also get a decent prediction. So if we were to do linear, let's just add it just to practice. So we'll add a linear trend line and we'll display the equation, r squared. It's not bad, but it's not as good as the curved equation. So, okay. This is on units. That's the 0.736 that we just figured out by adding in this trend line. Again, it's not bad. Our coefficients are significant, but let's see what happens. So they did two things here. They squared the units and they took the log of them. So they just tried two different transformations. And the formulas for those, so that's the formula to square the units. And then the natural log, the function for that is this ln function here. And then you would just plug it in and drag it down and you get all your data transformed. So then you just, now your y values are still cost, and then you're running your regression against the squared or the logged units. So when they do the squared units, they get a slightly better r squared. And if you do it with the log units, you get slightly higher than the linear, but not as good as the quadratic, the squared. So the equation here, where you have a equals, some intercept plus ax plus bx squared. In this case, the coefficient for x, and then there's a coefficient for x squared. You get slightly better data. So, but now look at our, we have to run multiple regression when we do quadratic on the units and the squared units, so that we can get the coefficients for, so we have y equals 5,792 plus 98.35x minus 0.06x squared. So the larger that x gets, the more units we order, the bigger this factor becomes. And since it's negative, that's our economies of scale. It's pulling our predicted value down a little bit more the larger our x gets. So intuitively, kind of makes sense, but this actually would kind of, like when you start getting really large, it breaks down. So this is something to note. For the log equation, so we have our intercept and our log units. The equation for this is right here. So interestingly, our intercept is negative, but then we have some coefficient times the natural log of x. And so this is telling us that when units increase by 1%, then cost increases by some given amount. So that amount is the coefficient of the log units multiplied by 0.01 or $166.54. So there's some increase. Each percent increase has a given amount that correlates to the increase in cost. So if I had to pick between the three, I would probably actually, even though the R squared is higher here, intuitively or from an interpretation standpoint, this regression makes the most sense and is probably a better predictor in a broader range of quantities. Okay, other nonlinear data that you will encounter a lot in manufacturing or original equipment manufacturing is learning curve data. So in production, there's generally learning curves. So as you manufacture units of some material, the first couple of units are slower, and then you get more efficient, and your future units are faster, and it's an exponential curve. So for learning curves, we always take the natural logs. And let's go to okay, so we covered this. So learning curves, unit of production time or cost relative to the cumulative volume of output since you started the process. So this is a known phenomenon. You can, like Boeing, Lockheed Martin, they all can, Raytheon, all their production time is decreased by a constant percentage every time the output doubles. And we call that the learning rate. So the learning rate has its own formula, which we can calculate in Excel. And we can use multiplicative regression to estimate learning rates for production time. So a data set that has batches, times, and then we can take the log of the batch number and the log of the time and plot log in log space. So both log, the log of the independent and dependent variables. When we do that, we get this nice linear relationship. So that tells us that there's definitely a learning curve going on here. When you run this, you can get your equation and then plug it into the formula and get the learning rate, which involves taking the anti-logs. Looks like they didn't do it here, but I might be able to tell you what it was. Okay, so if we were to do that, if we were to solve for the learning rate and take the anti-logs, it would be 0.898 or about 90%. So whenever you double production, the time to produce a batch decreases by about 10%. What else? I think for learning curves, that's really all I want to. I don't want to get too crazy into it, but I do want you guys to understand the concept of the learning curve and how it might apply. Okay, so unfortunately for us, regression analysis is usually pretty optimistic. So if we're trying to figure out if it would be successful in predicting new values, this is what I was talking about before. We need we need to split our data into some training data and some validation data. So we fit the regression equation to the training data. Then we substitute in the explanatory variables for the data from the validation set, and we see if we compare the predicted values to the known values of the validation data, and we see how well the fit holds. So if we wanted to validate our original regression at Bendrix for making predictions at another plant, so we're trying to predict overhead costs for another plant, but we're using the regression that we used for this, the original Bendrix plant. We're going to sub in, we're using that regression equation, but we're going to sub in the data from the second plant and see how well the regression from the first plant fits the data from the other plant. So if we did that, we'd have our validation data, which they provide here. So they gave us some new data, and then we run our, this was our original regression. And when we run them together, we get, let's see, let's make sure. Okay. So when we run the new data and we rerun we recalculate, sorry, our R squared. So to recalculate it, we're gonna take the correlation of the predicted value and the fitted value. And so from our original equation, these were the original values, the standard error and the R squared. They just pulled them over from the original regression. And then when we calculate the new R squared, remember that R squared is the correlation squared. So we can use that correlation function and compare them. So you can see it's not as good. There's a higher standard error and a lower R squared, but this is still a pretty decent R squared. So this is we can feel pretty confident that we can generalize our regression equation from the original plant data to other plants. If this R squared was really poor, then we would not have the same confidence that we could generalize the data. It would be specific to that plant. We wouldn't be able to apply it to other plants. So I hope that makes sense in terms of validation, because you as an analyst or future analyst, you will never model anything without splitting your data into training and validation sets and running your analysis this way. So, okay, let's take a break. Let's come back at 2:20, and then we will go through chapter 11, and then we'll talk a little bit about your discussion. Okay. Okay. Hopefully you guys are hanging in there. Let's go through 11. 11's, I'm gonna go, I think, a little bit faster. We're just gonna carry the concepts from chapter 10 forward and combine them with what we've talked about in the past in terms of like sampling distributions and population distributions and error and confidence intervals and so on. And what does that even mean when we're talking about regression? So we make some assumptions about our variables when we run regression models. And in chapter 11, they focus primarily on the population regression model. So what are we inferring? Like when we, for example, when we ran the data on warehouse, we pulled a sample of 36 months. But if we pulled a different sample of different 36 months, we get slightly different values. So that's what we mean by we calculated the intercept and slope terms, but then we're kind of inferring that from our sample, we can apply those same intercept and slope terms to the population. We want to know which explanatory variables belong in the equation, and whether or not there's any population regression equation worth pursuing. So can we take a regression equation from our sample of data and apply it to the population as a whole? And then we talk about prediction. So the whole point of doing the regression was to predict values of the dependent variable given new observations. And then what is the prediction interval? How accurate will our predictions be? Let me go to full screen here. Okay, so just like before, when we develop a statistical model, we make inferences about the population, and therefore we make assumptions about the population. So these assumptions basically are saying that we're living in a bit of a fantasy land. We're never going to fully satisfy these assumptions. Just real life is messy, but from a practical point of view, can we closely approximate to reality? And if we grossly violate these assumptions, then the inferences based on those assumptions should be viewed upon with suspicion. So in a regression, we assume that there is a population regression line. And what that means is the population regression line joins the means of the dependent variable for all values of the explanatory variables. And for any fixed values of the explanatory variables, the mean of the errors is 0. In very broad terms, we're saying that when we run a regression on a subset of a population or some sample, there's some error term that's going to be introduced, which corresponds to this like ideal population regression line. For any values of the explanatory variables, the variance of the dependent variable is constant. And normally, the dependent variable is normally distributed for any values of the explanatory variables. And the errors are probabilistically independent. Okay, so our population regression line assumption is important. It's implying that for some set of explanatory variables, there's an exact linear relationship in the population between the means of the dependent variable and the values of the explanatory variables. So that perfect equation would look like this. This is the mean of y given all of our explanatory variables. And alpha is our intercept, and then the betas are the slope terms. They like to use Greek letters when we're talking about unobservable population parameters, so that's why they're there. Most of our individual y's do not lie on the population regression line, this perfect line. So the vertical distance from the regression that we got to this line is the error. And so that's this error term here. So we have to compensate for the difference between the individual y's and the fact that they don't actually lie perfectly on the population regression line. Okay, so let's talk about variation around the population regression line. So regardless of the values of the x's, the variation of y about the regression line is the same. This is called homoscedasticity or constant error variance. And we can actually, when we run our outputs in Excel, we can actually look for this and we can see if this is true. I will say generally as your x increases though, the variation in y usually increases a little bit, and that's okay. Heteroscedasticity means that the variability of y values is larger for some x values than other, or it's non-constant. So this is what this looks like, because those are a lot of words. Words are great, but same thing I pointed out before. In my very horribly, I can't even, that was terrible. Pretend that's a straight line. So see how these points, as with the lower values of x, are clustered more closely around our prediction line, and then look at the differences between our values here. Much greater variance. So when you look at a scatter plot and it looks like this, you generally know that you do not have homoscedasticity. I can't even say it. And one of your key assumptions has been violated. Okay, so what does it mean to say that the errors are normally distributed? This is where we look at the residuals. We look at a histogram of the residuals, and then we should get a normal looking histogram in that case. If the histogram of the residuals was skewed, then that would probably indicate some, well, it violates this assumption here, but you would have to go back and look at your data. Okay, and then finally, the probabilistic independence of the errors. So the information on some of the errors doesn't tell you anything else about the value of the other errors. With cross-sectional data, this is just generally true. So we don't even think about this. The only time you really think about this is with time series data because of autocorrelation, which we talked about before. So autocorrelation means that previous values of time variables are correlated to future values of time variables, which means that the errors of the variables at earlier points in time provide information about the errors of variables in future time. Another assumption, no explanatory variable can be an exact linear combination of any other explanatory variables. So basically, this is a weird way of talking about multicollinearity, but it's basically saying if you have one variable that can be described by some weighted sum of the others, or it can be described by other variables, then you can't use the variable that can be explained by other variables to predict the dependent variable, because then you'd have redundancy in your data. So generally they're not exactly correlated like this with exact multicollinearity. So we only talk about multicollinearity, which just means that two of the variables in the data are highly correlated to each other. So for example, if I'm trying to predict the cost of energy on a military base, and I have several variables, and one of them is let's say one of them is square footage of housing, and another is acreage of land. The square footage of housing and the land acreage are going to be very correlated to each other. So the more housing you have, the more acreage you have. So you can't use both those things to predict energy usage, because you're kind of artificially like inflating the predictive value of your equation. It will look better than it really is, and everything will fall apart later when you're trying to do actual predictions. So you have to choose one. So you, if you're doing multiple regression, you need to check the correlations between the variables that you're regressing, the independent variables, to make sure that they're not basically just different ways of describing the same thing. Hopefully that makes sense. Okay, So that said, all I want you to take away from this is the concept of parsimony. We prefer models with fewer explanatory variables. So if you have a model that explains that predicts an dependent variable nearly as well as a similar model that has additional explanatory variables, you should always choose the model with fewer, even if it's slightly less favorable when you use it on your training data, because there's just, every time you add a explanatory variable, you add another error term, unknown population error term into your equation. And so you're just adding more variability in the data. Okay, so the sampling distribution was derived from the sample data, and it's the distribution of whatever we're estimating over all possible samples. So in terms of a regression coefficient, we use the t distribution, and if the t distribution, if all those regression assumptions are met, normality and homoescedasticity and everything, then the standardized value is this formula right here, and it's a t distribution, and it has n minus k minus 1 degrees of freedom. So what this is saying is that our estimate B is unbiased, meaning that there's some true but unknown value of the slope, and that the standard deviation of the slope is labeled S sub B, and we call this the standard error of the regression coefficient, and it measures how much the different slopes would vary from sample to sample. So in other words, if we took plant data from different months and we ran the same regression equation, we get different values of B each time. So we're trying to figure out how much those slopes vary. If they vary wildly from sample to sample, that's bad. That's telling us that our regression equation is probably not very good. And so we would look for the shape of that distribution of B's to be symmetrical and bell-shaped. And as far as like calculations and everything go, we're not going to get into any of that. Our regression analysis does all of this for us in Excel. It does what's called analysis of variance, or ANOVA. It's included. So we can make inferences about the regression coefficients using the outputs from Excel. And in this case, since they're doing multiple regression, they use stat tools, but the output's very similar. So let's see. Those t values are right here. So all that, there was a lot of stuff that we didn't really talk about before, but that's what this column right here is telling you. Those are the t values. And then where's our standard errors? Our standard error values are here. So it gives us that. And just as a side note, it also gives us confidence intervals at the 95%. So each B, or slope, represents a point estimate for the population slope, and the standard error of each sample slope is just indicating the accuracy of this point estimate. So the standard error here is telling us how accurate these coefficients are. Okay. One second, I just realized. Okay, good. Sorry. Checking something. Okay. All right. So we can use sample data to obtain a confidence interval for those regression coefficients. So our confidence interval is the slope for that regression coefficient plus or minus the t value times the standard error. So that should sound familiar from last week. We always get, it generally just always runs the 95%. So like for machine hours, our coefficient was 43.53, but the confidence interval is anywhere between 36.2 and 50.8. Okay, so we talked about the p-values. That's telling us whether or not the likelihood that, so our null hypothesis is that this is 0, this coefficient. And we're trying to reject that. We're trying to say, no, it's not 0. This variable is significant to the regression equation. And so that's what we look at the p-value for. And we practiced calculating p-values last week, but it does it for us. So if a variable's coefficient is 0, there's no point in including it in the equation. So we have to check those p-values and then make a decision. If the p-value is very high, it's telling us that that variable is not adding any value to the equation. Okay, so it is conceivable that none of the explanatory variables in the regression equation explain the dependent variable. One way to know that is by having a poor R-squared value that's low. Or it doesn't have any explanatory power if the same value of y will be predicted regardless of the values of x. So the null hypothesis then for the whole equation is that all of the explanatory, the coefficients for all of the explanatory variables are 0, meaning in this equation that this is actually 0 and not 43.5 times the number of machine hours. It would just be 0 times machine hours, which means machine hours becomes irrelevant. And then same thing for production runs. So to test that, we need to do a similar analysis for what we did for each coefficient, but now we need to look at the overall fit for the entire regression equation. And for that, we use the F-test. And let's not get too hung up on what that is. So ANOVA calculates variation several ways. They calculate the total variation of y, which is SST. So that's the sum of the squares of the total. And then they calculate the part that's unexplained by the regression equation, which is the sum of squared errors, and the part that is explained, which is the sum of squared of the regression. So these SST, SSE, SSR, the total explained variation is equal to the total variation in y minus the unexplained variation. So that said, we can take the mean squared regression and the mean squared error, which again, Excel does all of this, and we can calculate a ratio. So if we divide the sum of squared of the regression by k, and then the sum of squared errors by the degrees of freedom minus 1, we get the mean squared error. The ratio of these two tells us whether or not we have a good overall fit. So if the F ratio is small, the explained variation is small relative to the unexplained, so that's bad. If it's large, that means that the explained variation is high relative to the unexplained. So you want the ratio of explained variation to be much higher than the ratio of unexplained variation. That's all that's saying. The F ratio that you get from the output has an associated p-value that tells you whether or not the equation as a whole is also valuable. So if we go back to, actually maybe it comes up here. Oh, it doesn't. Okay. So if we go back to this regression output, which I'm sorry, it's so small. But down here, so this is our ANOVA table. Explained, unexplained. our ratio so that they calculate out the sum of squares for the explained and unexplained and then the mean. Our F value is right here and our P value is right here. This is a nice high F value and it's significant, so we can feel good about this equation. So it's a lot of things to consider when you run regression. You need to look at your coefficients. You need to look at whether they're significant, their errors, their confidence intervals, and then you're looking at the regression as a whole by looking at the F value and the P value for the F ratio. And we're looking at the R squared. So there's a lot going on. And then we're comparing the R squared to the adjusted R squared, in which case they're close. So yeah, there's a lot of things to consider when you're doing regression analysis. All right, go back to multicollinearity again. So fairly strong linear relationship among the explanatory variables. There's multiple degrees of multicollinearity, but in each of them, there's a linear relationship between two or more of the explanatory variables. So sometimes you can have a bunch of variables that are collinear with each other. And so you'd have a high degree of multicollinearity in your regression. And there's a couple of ways to identify if you might have this problem when you do multiple regression. So coefficients would have the wrong signs, so negative signs, or when you would expect them to be positive, or positive signs when you'd expect them to be negative. Smaller than expected t values, or larger or insignificant p values. Okay, so we're going to look at height versus foot length to see if we can create a regression for height. And we have two explanatory variables, right foot and left foot. So we generate some hypothetical data, and we say that height is approximately 31.8 plus 3.2 times the foot length. So that comes from here. When we run the regression output for that data, with left and right, we get pretty high R squared. So right off the bat, like, look at our F value, things kind of look okay, but look at here. When we look at our regression coefficients, we have a high P value here. 0. Ooh, look at our confidence interval here. Look at -3 to 1.3. 0 is included in our interval. That's a bad sign too. It's telling you you could probably drop this variable. And then the coefficient is negative. We would not have expected that because we're trying to imply that the larger your feet are, the taller you are. So looking at this, hopefully you can see how, as you go through each step of the regression analysis, you start to identify potential issues. And in this case, this is like very strongly indicating that left and right feet length are correlated, and they should be. They gave you, I mean, that's just a very like easy, obvious example. But that's how you would identify multicollinearity. So we can use these t values to help us make include or exclude decisions. So if we're trying to find the best explanatory variables in our equation, this actually can get really tricky. There's different philosophies on, or different like processes for which order you should go in. In the graduate data analytics courses, we actually talk about and compare different methods for doing this, like stepping in, stepping out. You can do it by the one that has the highest p-value, drop it, then run it again. So basically trial and error. So there's a lot of ways. And if you have 5, 6, 7 or more explanatory variables, think about all the combinations you could have between, it's a factorial number of combinations. So you get this possible huge amount of potential combinations of explanatory variables for your regression. So which ones do you include? Which ones don't you? We're trying to use the fewest number of variables possible. So now we're presented with a trade-off. How do we do it? We can look at the t-values and the p-values. So if a p-value is above an accepted significance level, which I've never seen as anything other than 0.05, then we could say, okay, that's a good candidate for exclusion. If the t-value is less than 1 or greater than 1 in magnitude, if it's, I don't know, I guess that's another way. If we look at this, in this case, our p-value would indicate we should drop the left, but the t-values indicate that we should drop the right. So that's fun. For height, though, prediction, it probably doesn't matter really which foot you pick. It's going to be left or right. They probably work pretty well, just not when they're together. Look at t-values and p-values rather than correlations when we're making include-exclude decisions. So pick one and then stick with it. An explanatory variable can have a fairly high correlation with a dependent variable because of the other variables in the equation, it might not be needed. It's redundant. So left feet and right feet with lengths are just redundant in this case. They're both great predictors, but one of them isn't necessary. That's the whole point of this exercise. So some other guidelines, if a group of variables are logically related, then we might include or exclude all of them. And then economic and or physical theory. Yeah, now you're getting into less scientific methods, but like the way that I walked you guys through it is how I would have done it. I would have looked at these coefficients, notice the high p-value, notice that 0 is included in the confidence interval, and I would have dropped the left and stuck with the right. Okay, so let's try to figure out, based on some data, we have some training data and then some validation data. And we're going to start with all of the potential explanatory variables and then exclude based on their t and p values. So here's our data. Age, gender, whether or not they own a home, salary, and we're trying to predict amount spent based on all these other things. So let's run it with everything. Not a terrible R-squared, but and overall, but we need to look at the coefficients. So looking at this, you go here. Let's just highlight things that don't look right off the bat. Notice these all have 0 included in their confidence intervals. This one has a t-stat that's troublesome too. Okay, so this is probably a good place to start. That's where I would start. You could also look and see if any of these are correlated with each other. So age doesn't have any strong correlations. Let's look at gender. I'm looking for high. If anyone spots a high value, let me know. This is kind of, we're ignoring amount spent. That's what we're trying to predict. This is so hard to look at. Salary and owning a home. That's potentially, we probably wouldn't want to use those two together. What is this? Salary and married. That's a high correlation. So those are multicollinear. Okay, here's another one. Salary and previous spent. Okay, so you can kind of see what I'm doing here. I'm just looking at this initial run and kind of looking for things to get rid of. Age, gender, own home, married. Okay. If I had to drop something right off the bat, I'd probably drop gender. There's, again, this is so open. So it looks like we dropped gender, whether or not they own a home. They dropped all of the married and age. Okay, so they dropped every single variable that wasn't significant. You could do it one at a time and then see if these become significant. So I don't know, but in this example, they just immediately tested out all of the high p-values. So they said, okay, we're not going to use these because they're not significant. They might as well be 0, according to our regression. All right, so now we're left with these ones. Now all their p-values are good. And these are some really high t-stats. Again, I'm looking for stuff in here that's high. I probably don't need this. So previous spent is highly correlated with both salary and previous customer. So that would tell me that it's pretty redundant, and I probably could stand to drop that one. What else? Ooh. Oh, that's just the same. Okay, so that might be a good next one. But they actually don't. They're happy with this. In my opinion, I would drop that. But they were happy with all the p-values being significant at this point, I guess. So then they took their validation data. They took the equation and they used that to predict, given the amount spent. They have the predicted, and you can go in and look at the formulas to try and see what they did. But they basically just took the equation and then calculated based on the amount spent what it would have been predicted. So, and then the error. So the equation predicts for, for these given variables that the amount spent will be 2,105, but it was actually 2,183. So it came close, within $78. You can see the error, varies quite a bit. Some of these are really close. Look at this one, was only off by $4. Some of them are off by a lot more, and that's normal. Ooh, some of them are really off. There might be an outlier or an outlier-ish. Maybe not. I see some high ones. Anyway, so now we have the predicted versus the actual, and we can calculate the R-squared for our prediction using our validation data. And when we do that, we get 0.732. So that's great, because our R squared from our regression was 0.746. So our validation data, our equation held up pretty well. It calculated the validation data nearly as well as it predicted the training data. So that's what you want. I think that's all I want you to take away from that one. It looks like, okay, so this was a different methodology. So this is what I was saying, you could do it one at a time. So they went backwards, stepwise. So this is called backwards stepwise regression. So you take out the highest p-value item, run it again. Take out the second highest p-value item, run it again. Take out the third, the highest from the new set each time until all of your coefficients are significant. And then check your F is high, it's significant. So the overall equation is good, the R squared is good. So with this approach, you get a slightly better mixture of variables. So comparing the two, looks like there's, oh no, they came out with the same. Interesting. Oh no, it's the same. Oh, okay. I guess it's just showing you step by step, I guess, how they did it. I was thinking they did something different, but look at the residuals though. Interesting. Okay. Actually, so going back to the salary data, this is with all the data running for all of these variables. And then what did they do? Oh, outliers. Okay, so okay, we talked about stepwise. So you can go forward. So the steps that I showed you were backwards, where you start with the highest p-value and then subtract out one at a time. You can go forward where you start with no variables and then you add one at a time until they stop contributing. But that's a lot harder to do because there's a lot more like trial and error. I think there are, yeah, never mind. I don't want to go down that tangent. Okay, so we talked about that. Okay, so the last subject for us, I think, is outliers. So an outlier is an extreme value for at least one variable, and if the value of the dependent variable is much larger or smaller than predicted by the regression line, and its residual is normally abnormally large in magnitude. So for example, this outlier here, or potential outlier, has a really high error here from the regression line. So we would want to investigate that data point. It's likely an outlier if not only the residual is large in magnitude, but it affects the regression line. So that type of outlier that drags the regression line up or down is called an influential point. So remember we looked at the salaries and the CEO salary was like really high. So he's skewing the regression upward. If we took that point out, we'd have the line without this outlier and the line with the outlier. So if that happens, just by removing one point, there's a good chance that you have an outlier, or a true outlier. Sometimes it just doesn't fall within the general pattern. In that case, it might make you feel good to remove the outlier that you perceive because it doesn't look good, but it may not be appropriate to do so. So when we want to examine data points to look for potential outliers, we can look at the box plots to help find potential outliers, but also we can look at the residuals and see if there's any residuals with like abnormally large values. So these are two ways to do it there. And I think I don't know if we need to get too. So yeah, I think you can go through the examples in the book, but I think I just want you to understand what they look like and how you might identify them. So in this graph right here, this data point right here is worth investigating. So you can run, actually this one right here. So you can run the same regression with the outlier and then take it out and run it again. And then you can look and see. So see that R squared improved by a little bit, 0.73 to 0.75. So that outlier didn't have like a terribly massive influence on the equation, but it definitely did increase the variance enough to influence the R squared. So yeah, I think it was this one that they removed down here. The problem with doing this is like, you can go down this black hole of like, well, now this point looks especially bad, and you end up removing data that isn't warranted. So you have to be careful with removing outliers. You're generally safe if you stick to this process only once. So if you look at the residuals and you use that to determine whether or not something might be an outlier, then don't do it again to find potentially more outliers. So we would kind of ignore this residual plot here and just use this new equation. So the coefficients changed from one to the other, and it's too hard to flip back and forth and compare, but you can see like the values are different now that we have that outlier gone. So we have a slightly better regression equation. So that's all that is. Removing outliers is a tricky thing. Always document what you remove too and your justification for removing it. Okay, so violations of regression assumptions. How can we detect them? Pretty easily. We showed some ways of seeing violations with the scatter plots, the histograms, especially the residuals, by looking at a time series graph or other numerical measures like the p-values and t-values. So if violations are ignored, sometimes it's fine and sometimes it's not. It really just depends on how severe the violation is. There's always going to be some minor violations of assumptions, but what to do about it is the tricky part. And if we violate the second regression assumption that the variance of the error should be constant, mild violations don't really affect the validity of our output, but really large violations do. And we can see that when we look at the that fan shape in the scatter plot, where everything was nicely scattered about our regression line close with small values of X, and then the larger X got, the more the error increased. So that type of fan shape is one indication that we have a violation. And it makes the hypothesis test for the coefficients invalid. So we we can't have confidence in our regression equation. So we can use a different type of regression methodology, or we can transform the dependent variable into log space. We're not going to get into other estimation methods. This just for your knowledge. There are sometimes ways to transform data in order to be able to use it for prediction and for regression, but that's how you would identify it. That fan shape generally means we violated the second assumption. The third regression assumption is the one that says that the error terms are normally distributed. So we take a histogram of the residuals, and if it's non-normal, then we have to take our outputs from the regression analysis with some caveats. They might be approximately valid. It kind of depends on how badly skewed the residuals are. We can also fix this a lot of times by doing logarithmic transformations. So there are things that can be done. I actually have a really cool, I wonder if I could dig it up. I have a really cool chart about residuals and like the shapes they make and what they mean. I'll look for it here in a second when we move on to the discussion, but okay. And then autocorrelation and time series data. So there's a statistic that can be run. Don't worry too terribly about this. You can look over this example. We're not going to calculate this, but if you were doing analysis on time series data, this is something you would want to come back to. There's a test called the Durbin-Watson statistic, and it tells you whether there's any like lag in your data for the residuals. So it just basically just checks for autocorrelation. And then now if we have a regression equation, we've checked it out, everything looks good, everything looks promising, we can use it to predict the value of the dependent variable for new observations, either for one or more individual members of the population, or we can predict the mean of the dependent variable for all the members in the population with certain values of explanatory variables. So when we predict a mean, there's a single source of error. So predicting the mean for all members of the population is generally going to result in a more accurate prediction. When we predict individual values, we have errors on the regression coefficient and the variation of the individual points around the regression line. So that looks like this. So here's our estimated regression line and the population regression line. The prediction error for the mean is just the difference between the two at the mean, these 2 points at the mean. But for any given point, we have the prediction error for the individual value and for the line itself. So this is a really bad way of showing it, but what they're really trying to tell you is that when you predict values of X that are close to the mean of the regression, they're likely to be more accurate than when you predict X's beyond the range of your data set. So we call that extrapolation. So you have to be very careful with that. So for example, if I'm trying to predict the cost of my ship engine, and I have weights for ships that range from 1 ton to 10 tons, clearly I know nothing about ships, then I can't use my prediction to extrapolate the price of a 20-ton engine because I'm outside the range of values that I used. If I wanted to do 5, that would be within my range of 1 to 10 or like 7.5. Maybe even could get away with 11. But the further you creep away from the range of data that you use to create your regression, the riskier your prediction is. So yeah, to predict, you just plug in your value. So in that case, if I'm predicting the cost, I get some regression that's like A plus B times the weight. I would plug the weight of, let's say I'm doing 7.5 tons, I'd plug that in as X. and then see what it gives me for y for the cost, using the slope and the intercept for my regression equation. Finally, we can do confidence intervals for individual values and for the mean. Individual values, we usually use the term prediction interval. At least I know for my industry, we do. So we would say the prediction interval for, so if I was estimating a 7.5 ton weight, that I would give the prediction interval for that individual point rather than calling it a confidence interval. But the interpretation is the same, they're just calculated slightly differently. I don't think I want to go through this last example, but you guys can if you would like to. Okay, so let me dig up, well, actually here, let's do this. What was our discussion? Okay. Yeah, these are just kind of, make sure you go in and answer these. I actually don't, I would rather just take questions because these are just kind of reinforcing, your discussion questions are the conceptual questions that reinforce what we talked about today. So I'm going to ask if you guys have any questions, and then I'm just going to check something really quick with the homework. Yeah, so you have just 2 examples to work through. Try them. I will plan on setting some time aside on Sunday. I do have a coworker in town for a project, so my Sunday availability will probably have to be later in the day, but I'll record that session and make it available. And then it's okay if you get stuck and you need to wait for the recording and then you need an extra day to do it, that's fine. But just follow the book, follow the examples in the book. I picked some of the more simpler examples just to get you guys used to running and interpreting what we talked about today. So that's that. I'm going to go ahead and stop sharing for a second and look for the slides that I really want to show you, and then I'll give you guys a chance to share your thoughts or ask questions while I'm looking for that. Oh, I know where it is. No questions?
No, I don't have any. You're right. It's just things we went over in things you already talked about.
Okay. Any questions about the material? Sorry, I'm logging into this thing so I can show you something that I think is a lot more helpful than the book. If I can't pull it up here in the next minute or 2, I'll just share it, but via an announcement or something. But let's see. Where is it? There's a association called the International Cost Estimating and Analysis Association, which certifies cost estimators and analysts in all over the, well, it's actually international, so all over the world. And I have, there's a body of knowledge that covers, there we go. A lot of the topics that we're talking about in this course, but then also goes into like very specific things about cost estimating. But there is a section on regression analysis, and we talk about the residuals and looking for patterns in the residuals. So let me share my screen one more time just to reinforce this. So this is our body of knowledge, which talks about like correlations. So a lot of things interpreting the ANOVA results, and then I found it, yay. Okay, so this is a good residual pattern. Constant variation, it's kind of centered around 0. If they look like an arc, then a curvilinear model is probably better, like the quadratic or the exponential. If the residuals are non-constant, they will have the same fan shape as the original scatter plot of the data. And that was where they were talking about trying like a weighted least square. So just a different regression tactic that's more advanced. So this shape is not good for the standard linear regression, but there's still potential for that data using a different methodology. And then if you see residuals like this, where they kind of follow trends, that actually indicates that you have loss of learning or injection of new work. So there might be learning curve data in this. So anyway, I just wanted to show you that. I like this graphic a lot. I think it kind of helps reinforce what when they say like, look at their residuals and look for homoescedasticity, like that's what this looks like. It's nice and even and uniform. And if it's not, then you kind of know which approach to take depending on the pattern of the residuals. So you can learn a lot from that graph of the residuals about your data and whether or not your model is appropriate. So that's all. I'm not sure. Pretty cool. I made that graphic, so kind of proud of it. Okay, I'm going to stop recording.